So the quiz yesterday is, basic electron configuration stuff, like how many electrons can be held in the s orbital. That's 2. How many orbitals are in a p sublevel? That's 3. So the p sublevel can hold a total of 6 electrons. That kind of thing. So hopefully you got that done yesterday. And it sounds like you guys were able to get that done and then go to the gym. Show me your muscle. Huh? You sore from it? What is your routine? What do you do to get pumped? Did you pull down the things over your back like this, or did you push up the things like this? Oh, incline. So like incline bench. Were you rested back, or were you straight up and down? Do incline, yeah, versus doing shoulder presses where your back is at like a 90-degree angle to the earth. You did incline benches. What are you trying to get that? Because that does the top of your pecs right here. You're trying to get that big old like Hulk Hogan or this full body. Cool. Kaz got a new exercise routine that he's been checking out. What else did you guys do this weekend? You're gonna get that door back there for us, Kyle. That guy talks too loud next door. What'd you do? Just at home chilling, like some Netflix or what? Hulu. What are you watching on there? Prison Break. Which season are you on? Number 2. So you're almost done. Because nobody should go past number 2 of Prison Break. It gets a little bit ridiculous. Season 3. You'll see. You'll see. How about you? What did you do? Anything fun? Yeah, it wasn't like I tried to just want to throw, like I wanted to throw a snowball at somebody really hard and it just did not stick. I had to actually put a rock in there and then get the rock wet, and then I was able to get it to stick enough around there. Anything else? I didn't hit anybody with it. No. How about you? Nothing? Sydney, what'd you do?
I mostly just watch TV. That was pretty much it.
Yeah. Are you watching Prison Break?
And no, WandaVision.
WandaVision. Did you watch the newest one? No spoilers. I haven't seen it yet.
Yeah, I watched the very new one. It's good.
Yeah, right. I thought the last week's was amazing when they kind of revealed some stuff, and I was like, "What? Oh no!" But yeah, okay, yeah, it is very good. What's that? Oh, careful, careful! Spoilers. Last one I watched was the one where they showed how color got into the world. Am I 2 behind? That's what I was thinking. I was like, I think I'm just 1, or maybe 2 behind. I got a PS5. I don't have time for all these shows anymore. Right? That's how I roll. Huh? That's how I roll. You're playing at Miles, huh? That's my jam right now. You got off track so much? Oh no. Password? You're gonna have to get back on it. All right, let's see what we've got then. Everybody's caught up with everybody's weekend. Yesterday, we had an asynchronous day. Tomorrow's Friday, and this week's done. We got a weekend coming up. So, my notes say that we need to work on some math problems. So get your calculators out and open it up to the page where we're finishing up these math problems. Let's take a look at it. Boom, 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 boom. Boom, 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 boom. Is that okay? That's good. So here we're given wavelength. Now that is a Greek letter lambda. So that lambda can go here or here. Since we're trying to find the energy of the photon, it only makes sense to use this formula. So if we're calculating the energy of the photon, we know Planck's constant, we know the speed of light, and we know lambda. So basically, I'm not even going to bother writing that out because I'm going to take Planck's constant, which is right here. 6.626 times 10 to the negative 34th. I'm going to multiply that by the speed of light. And then I'm going to divide that by lambda, which they've given us. That gives me 3.03 times 10 to the negative 19. Now the cool thing is that this is joules per second. This is meters per second, right? And the wavelength is in meters. So meters will cancel out and seconds will cancel out and we'll end up with joules, which makes sense for energy because joules is a measurement of energy. All right, down here, basically all we're doing on this each time is we're taking this number and we're dividing it by the square of the energy level we're at. So that will be 9, this will be 16, and this will be 25. So negative 2.18 times 10 to the negative 18 divided by 9. That gives us negative 2.42 times 10 to the negative 19 joules. We'll just pop right back up there and we will divide that by 16, which gives us negative 1.36 times 10 to the negative 19 joules. And we'll pop back up there and we'll divide it by 25 because that's 5 squared. It gives us 8.72 times 10 to the negative 20th joules. So that's how we do each of those. Then it says, out of these energies, which one is the lowest and which one is the smallest? Well, all of these are negative numbers. The negative number that is closer to 0 is actually a greater number. A negative number that is closer to 0 is a greater number. So if we take a look, this is 19 zeros and then an 8. This is a very, very small number. It's negative. Since it's negative to the times 10 to the negative 20th, that is actually bigger because it's closer to 0 than times 10 to the negative 19. So in reality, this is the smallest number there because it's negative 2.18 times 10 to the negative 18. So if we look at that without the negative sign, this is bigger. But when we put the negative there, that means it's further away from 0, which means it's really, it's the smallest of them. So that is the first one, second one, third one, fourth one, and fifth one. As we get further away from the nucleus, the energies get greater. So in order of increasing energy, it goes E1, E2, E3, E4, E5. All right. So it says from n equaling 5 to n equaling 3, find the energy of the photon. They give us an equation. What we said was if we have the nucleus there and an electron is outside of that nucleus, that electron will emit a photon whenever it drops back down. So this electron was at energy level 5 and it dropped down to energy level 3. Well, at energy level 5, it had negative 8.72 times 10 to the negative 20th. Oh, I already forgot that as soon as I said it. 8.72 times 10 to the negative 20th. That's energy level 5. Energy level 3, well, that is negative 2.42 times 10 to the negative 19. So now that we have these levels, energies, we can take and subtract them and find the energy of the photon. Those lines on the outside mean minus negative. That means absolute value, 2.42 times 10 to the negative 19. So we take the 8.7 and then we subtract 2.42 and it's negative 2.42 to give us 1.55 times 10 to the negative 19th joules. So here's the thing, it had this energy and then it dropped to the third level, losing this amount of energy for the photon. Well, the cool thing is that we can take that amount of energy and we can calculate the frequency or the wavelength of that energy. So I'm going to calculate the wavelength of it real quick. I'm going to do that up here. So the energy of the photon equals hc lambda. So using algebra skills that my algebra teacher taught me, I'm going to rearrange this equation by moving lambda up to the top and energy of the photon down at the bottom. So now I'm going to take hc 6.6262 6.626 times 10 to the negative 34. We're going to multiply that by the speed of light, which is 3.0 times 10 to the 8th. That's meters per second, and this is joules seconds. And the energy of the photon is this right here, is 1.55 times 10 to the negative 19. And that's joules. So joules and seconds are going to cancel out. We've got 6.626 times 10 to the negative 34. You're going to multiply that by the speed of light, and then we're going to divide that by the energy of the photon. What we get there is a crazy small number, which is 1.28 times 10 to the negative 6. And here's the thing. This is meters. This might make more sense to us if we can get rid of this times 10 to the negative 6. So every 1 meter is 10 to the 9th nanometers. You might have heard of nanometers before. It's a fraction of a meter. 1 nanometer is a billionth of a meter. When we're talking something about frequency and stuff like that, or wavelength in this case, you will deal with things like nanometers. So we're going to multiply this by a billion. And that gives us 1.28 times 10 to the third, which equals 1,280. Run around that. Nanometers. Right? So here's the thing with this, like when they talk about like X103, that's the frequency. In reality, X103 is 103.3 megahertz. That means that that radio antenna vibrates 103.3 million times every second. But we rearrange the decimal and we just call it the frequency is 103.3. To the average person, that units of that doesn't matter that much, but it is 103.3 megahertz. A megahertz is a million hertz. A million nanometers makes 1 meter. So what all does this mean to us? Well, let's take a look at the rest of electromagnetic radiation. Gas falls, organic. So what does that mean to any of us? Let's take a look. So here is electromagnetic radiation. Down at the very bottom, we said we have the radio waves, right? So we are in 1,000 or 10 to the third meters. So whenever that energy level drops from 5 to 3, it lets off 1280 nanometers. So if we take a look here, that isn't even close. We're up here more. So if we take a look, here's all of our radio waves, and here is our microwaves. Let's go ahead and convert this to centimeters. So 1280 nanometers. If we convert that to centimeters, we would be dividing it by, well, 1 times 10 to the 7. So that's even a fraction of a centimeter. That's not microwaves then, because that is 10 to the first or to the 0 centimeters. 10 to the negative first centimeters is the start of what we call infrared radiation, which is below red. And here's our visible spectrum. 10 to the third nanometers is our visible spectrum. So if we take a look, we can see stuff from 400 nanometers all the way up to 700 nanometers. 700 nanometers is red. Right there in the middle is like this yellowish green. And then we have the blue at 400. But we're not even there. We're at 1280, right? So that's going to put us at something right around here. In what we would call the infrared. So the near infrared is where we would be with that. If we take a look, if we go beyond visible, if we go beyond violet, we get to what we call ultraviolet. Ultraviolet, and then we have gamma rays and X-rays here and gamma rays here. Now the cool thing is that these are what we call our visible spectrum. This is the only thing we can see. If we take a look, see if I can do it. Do I have the battery power? Oh, don't have the battery power. Maybe. So if we take a look, this is a green laser. So this is going to be somewhere along the 500 nanometer wavelength. You take a look at any laser, they will actually tell you what the wavelength is. So you can see here, they give you right there, it says wavelength. So it's 532 nanometers, which would be right about there, 532 nanometers. And that's the color that this gives off. Take a look here. This is a blue laser pointer, right? You guys can see it up there. This is a blue laser pointer. So if we take a look here, It has the same thing. It says wavelength 405 nanometers. So if we take a look, here's 400, here's 405 nanometers. That's the deal with it. That wavelength, as we've talked about, just like sound is based off of different frequencies and wavelengths of a sound wave, lights, colors are based off of the same thing. So I'd like for you to do tomorrow is I'd like for you to finish B, C, D, and then do 5 and 6 down here where you actually take it just like I did up here and you find the wavelength. Cool, cool. 840. Let's take a look at, I've got something cool for you as well. Let's stop this share and let's start another share. Hopefully this translates decently well. If you're at home, you want to get somewhere where you're comfortable. And you can basically look at something. That's the key with this. Being able to look. If you can, close the curtains so that you're only focusing on what we're looking at. All right. So I'd like for you to do is to look right there at that little corner right there. Just stare at that for about 30 seconds. What we have here is a yellow box up in the right corner, left corner, and then we have these green and black lines. We're staying right at the bottom of that yellow box. What we're doing is we're saturating our tones. Our tones are what see the different colors. We're saturating them with yellow and cyan. Now, red and green make yellow. You mix red and green light, you get yellow light. Cyan is made from green and blue light. So we're saturating those, which means that we're dulling those indicators. So I want you to take a look at either the floor or a white piece of paper and blink a few times. What do you see there? What does it look like to you? So you're focused right here, right? Look right there, that little corner right there, for about 30 seconds. You're looking at me, can't be looking at it at the same time. And look at the floor or something like a white piece of paper and blink a few times. What does it look like? Yeah, you see different colors, right? It should look like the American flag. Up here, it should be blue, and these lines now should be red. Oh, you may have messed up eyes then. Do you have the proper rod and cones? Were you looking? Oh, yeah, that may be it. It's tough. Like, because then you won't actually desensitize them. That could be a problem. Let's try then this one. Take a look right there at that dot, that lower dot right there. Just focus right in on that lower dot. And then after you do it for about 20 seconds, then look down at the floor at a white paper and blink. What do you see there? What'd you say? You see Jesus? Yeah, right? You should see a guy, it looks like it's almost glowing, right? This time we don't have any colors because we're not messing with the tones this time. We're messing with the rods. The rods see black and white colors. So where this is white, you should see dark, and where it's black, you should see light. And it looks like a glowing symbol of, as you said, Jesus or whatnot. Now, these are some optical illusions. Like, for example, this ball right here is the same exact size as this ball right here. But when we surround this one with smaller ones, we think this one looks larger. And when we surround this one with larger ones, we think this one looks smaller. Same thing with these two doorways. This door and the door down here are exactly the same size. The one up top, because it seems like it's further away from us, we think that it is larger. Same thing with these two things, but if we look, this matches up with this, and this matches up with this. These are exactly the same size. If you were to print this out and then cut these out of the paper, you'd be able to see that they're exactly the same size. And here, it looks like C runs right between these two to most people, or that it lines up with A. In fact, C lines up with B. These are what we call optical illusions. Same thing here. These lines look like they're not parallel, but in reality, these nice black lines right here and here, they are parallel to each other. It looks like this one bends out and this one bends out as well, but they don't. They are parallel. Take a look here. Just a bunch of squares. But our brain sits there and tries to make something up where the squares meet, and we see these little gray dots between the squares. Right? You see them, but when you try to look at them, they do what? They go away. You see the gray parts between the squares? Let's amplify it a little bit. Take a look here. What's that? Messed up, isn't it? Yeah, you see these these like gray dots, but then when you try to look at one, they turn white immediately. Right? Take a look at this blue dot in the center of the screen. And just keep looking at it. Eventually, you should be able to make it go away. Then if you blink, it comes back. If that's too hard for you, then you can try this one. Stare at the black dot. See all the colors around the black dot? Keep staring at the black dot and the whole screen will turn to gray. And then when you blink, you can see all those spots again. This is basically what our brain does to kind of like lessen the amount of information that we're getting, because it's not necessarily important information. If you take a look here, move your head side to side or back and forth, and it looks like those move. If that's not working for you, let's try this one. This one's a little bit more effective a lot of times. It looks like stuff's moving if you move your head back and forth. How about this one? If we look closely, like we kind of see all these blocks. This is where our brains try to organize information. In reality, there's nothing that makes this block exist except for the way your brain perceives it. Right? This is seamless. But your brain sits there and says, okay, we're going to block this off into different amounts of information. We need to compartmentalize this. Take a look here. This circle, to most people, it looks like it's not a circle. It looks like it's oblong. or egg shape. In reality, that is a perfect circle. Or this one here, to a lot of people, the middle box right here appears slanted, almost like a trapezoid instead of a square. But in reality, it's a square. This right here, you see the spiral? Check again, it's not really a spiral. Look at this circle right here. This circle is just a circle. And this circle is just a circle. Our brain sits there and says, oh, I've seen this type of thing before. It's a spiral. But it's not. It's just a bunch of circles on top of each other. What do you see there? What does that look like? Like an E, right? Imagine a line right here. Then you got an E. What's her shirt say? It says love in the mirror. It says hate. It's all how we're perceiving it. What do you see here? What is it? You see a man with glasses, maybe? Well, what if I called you a liar? Right? If you can write cursive, then you'll see that this is an L-I-A-R. How about here? What do you see? What's this person eating today? It says it at the top. What's that say? Fish. Are you sure it says fish? It says girl, doesn't it? And now she's waving at me. Right? How about this? What's that in the pond? What do we call those creatures that sit on lily pads? Frogs or toads? You see the frog or toad? Or do you see the horse? Right? How about this? What city do you think this is? What's that? The Twin Towers? This is actually a circuit board. It's not a city at all. This is a circuit board. Back in the day, they used to make things that looked like something but really weren't. It was kind of cool to make it. Like, for example, you look at this and this looks like a peg. That peg comes back, but it's not three-dimensional anymore. It's actually making up the sides of this. And if we take a look here, what shouldn't be anything, as we go back here, it somehow becomes part of the whole thing, right? This doesn't make sense. Just like this doesn't make sense. It looks like over here, it looks like four pieces of wood may be stacked on top of each other. Let's follow this piece of wood right here. As we follow this piece of wood right here, it becomes nothing, which can't exist. Same thing here. Take a look at this foot of this elephant right here. In reality, that foot doesn't attach itself to the elephant, right? How many feet do we see there? 1, 2, 3, 4, 5 feet. Well, how many legs do we see? 4, right? So yeah, it's kind of messed up. So those were very popular. Read that. What's that say? A bird in the bush. But the first time you read it, you missed the first the. You're like 67% of people. Your brain sits there and assimilates it. Oh, that can't be right. It must just be a bird in the bush. Take a look here. A and B. A in our mind looks darker than B. In reality, this box that this B is written in and this box that this A is written in, they are the same color. To prove that, I'm going to put a box over both of them and you'll be able to see but that box does not show a line. So they are, in fact, the same color. Our brain sits there and tells us, well, B is in the shadow of that big green thing, so it must be a lighter if we're going to look at it like that. Same color, same color, same color. What's that? What is it? Louder? Death? Maybe. Anybody? What if I said moo? What says moo? Cow. You see the cow? How about now? Right? This one's a little easier. What do you see there? Yeah, it's a Dalmatian. There's a dog here. Here's its legs. Here's its mouth and head. Here's its little butt. You see the man? You see the man here? Does it look like a face at all? No? Nobody sees the face in this one. What about right here? You don't see that face? Right? These are some older ones. We have the lips kissing, and it looks like a vase as well. Or a man playing the saxophone and a girl's face. Or a rabbit or a duck. Old lady or a young lady. Two people sitting outside like an art or an arch. Or a man's face. Right? And the dog makes up kind of his hand over his heart. Here we have two lovers embracing in a kiss. Here's their mouths. Here are their eyes, embracing in a kiss. Or if you look, it looks like the beard of an old man here and the wrinkled face. Two kids playing with a dog or a skull. Two lovers embracing at dinner or a skull. Right? Is the man mad or happy? Squint your eyes and watch those faces switch. The angry one becomes less angry, and the one that's not angry at all becomes more angry. Oh, don't want to do the epilepsy thing. Like some of them blink, and I don't want you to have any issues with it. Here we have a man that draws basically things in New York. You can see he's drawn this, and it's just flat on concrete, but it has a three-dimensional perspective to it. If we take a look here, we see these red lines, but how many of you see these like weird black lines? In reality, our mind creates those black lines. They don't really exist. Here's another one that you stare at. You stare right at that dot in the middle. This is what we call a film negative. So what's going to happen is as this goes on, keep staring at the dot. As this goes on, it's going to switch to a black and white picture. And then we're going to actually see color. As soon as you blink, it goes back to black and white. Basically, we've hypersensitized your eyes again. So if you stare at it, we're going to see black and white, but we will actually get color. Right? Pretty cool. So if we take a look here, up at the top we have this cloud. Here we have the clouds. Here we have the man and his reflection. Like a monster as well. So that's all I've got for today, guys. Have a great day, and make sure you get those math problems done, please. And we'll see you tomorrow for Friday. Easy week. What's that? It's an old commercial.